Okay. So, hi all of you. So today in this session we're gonna start ISRO 2016 strength of material and machine design questions. So the first question we will see here. Just have a look on this. So this question is basically belonging to machine design. The main objective of short pinning is to improve which property of the metal parts, right? So when you look at the option, you have only in the options property. Let's say we have ductility and fatigue strength, right? Or it can be none of the above, like other properties, right? Like elastic strength or and all. So when you look at the objective of short pinning, the basic purpose of short pinning is to increase the fatigue strength, fatigue strength of a particular metal, right? Now, why and how we do this short pinning? Uh, that is the main objective of discussion here. So, note down. So, all of you must know that whenever we will try to learn, first of all, what is a fatigue strength. Fatigue strength. We sometimes also call this to be endurance strength of a component. Now, what is the definition of endurance strength? The definition is saying that the maximum value of the stress amplitude, right, or maximum value of the variable stress which a standard polished specimen can withstand for a minimum life of 1 million revolutions under completely reverse bending load, right? All of you know that we have performed, the Wohler was a scientist who performed the experiment by taking the case of completely reverse bending case, right? He was basically applying the load. This is the component, and he was applying the load that is continuously varying from tensile to compressive, right? Tensile to compressive. So here, this particular member is subjected to what? Let's say we are applying the load P, right? And we know that the bending moment diagram will be something like this for this case. If it is having a length of complete length of L, then we will be getting what? PL by 4. That is the maximum bending moment we can get. BMD diagram, right? But he was basically connected this shaft with the motor through the coupling, right? And the motor was basically rotating this particular shaft through which the component is subjected. And here we have connected this with some revolution counter, which counting the how many revolutions it is undergoing before failing, right? This is a revolution counter. I'm just doing the setup which was done by the Waller scientist, So this setup is done to determine the fatigue strength of a component, right? So what is happening? The first time when you observe the shaft, let's say this is the shaft, and when you focus your attention on A point, so when the shaft is there at this position, the top fiber at particular A point, based on the bending moment, this particular bending moment is what? Acting like a sagging bending moment. Then top fiber is under what? Compression. Again, the shaft is getting rotated. The shaft is what? Getting rotated. After getting rotated, point A is coming over here. The same point is coming over here after rotation of 180-degree. So what is happening? What is happening? The point A will be subjected to what? Tensile. Again, after rotation, it is coming here. Again, it is what? Subjected to what? Compressive bending stress. Again tensile, again compressive. Again tensile, again compressive. Of same magnitude but opposite in directions. Right. So he was got to know that when the material is subjected to completely reverse bending stress, then he concluded that what he concluded, the maximum value of the stress amplitude, this value of maximum value, maximum value of the bending stress by which a material is being subjected, right, through which the material is being subjected throughout of its life, the maximum stress amplitude which a standard polished specimen can withstand for a minimum life of 1 million revolution under completely reverse bending load, right? That particular strength we call endurance strength, right? No doubt. the maximum stress amplitude, the maximum value of the stress amplitude which a standard polished specimen can withstand for a minimum life of 1 million revolutions. Minimum life of 1 million revolution under completely reverse bending load. Under completely reverse bending loads. No doubt. That's why also you see the graph something like this. A general graph I'm drawing. I'm not drawing exact graph for a particular material. When you see here stress versus number of revolutions, you will see the graph tends to behave like this. As you keep on increasing the as you keep on reducing the load, see this is the maximum bending stress, right, through which a material is subjected. As you keep on, see how we can calculate the maximum bending stress. That is a very simple 32 m maximum divided by pi dq. But what is the m maximum? M maximum is what? PL by 4. Now, when I increase the value of P, my bending moment will increase. My bending stress will increase. My bending stress will increase. That means what? We are coming closer towards this particular diagram. That means the number of revolutions which can material can make before its failure will be lesser number of revolutions. But when I reduce the load, maximum bending moment will reduce because P will reduce, M will reduce, sigma will reduce. When sigma will reduce, then I'm getting what? Closer to the right side of the diagram, then the number of revolution will increase, right? When sigma will increase, number of revolution will decrease. When sigma will decrease, number of revolution will increase. That means when I keep on reducing the load, the number of revolutions a material is undergoing will also increase before it's going for failure, right? So we generally define the fatigue strength for low cycle fatigue component, right? Low cycle fatigue component. No doubt. Now, this failure phenomena and all basically happening when the material is subjected to tensile load, right? When the material is subjected to tensile load, right? All these phenomena are very, very severe when the material is subjected to tensile load, because in reality, you know that the material never gonna subjected to this kind of situations. Right now, whatever the experiment is there, this experiment, when you see this experiment, it is looking like the material will always subjected to completely reverse load, but it is not true. It is not true. In reality, the material is being subjected to what? Both static load as well as fatigue load, right? Both static load as well as fatigue load. Then how to solve and how to design that particular component when it is subjected to both static as well as dynamic load? Tell me this. How you will design the component when the component is subjected to both static as well as what? Fatigue load. Because in this case, when the material is subjected to completely reverse, then we know that sigma E, we know that endurance strength of a component, we know endurance strength of a particular component, right? And that is a 1 million revolutions approximately. It is a 1 million revolutions, and corresponding to 1 million revolution, whatever the stress will be there, that we call endurance strength, that we call endurance strength. But the problem is, here we know the failure stress, right? For a completely reverse load, for completely reversed, you know that the difference between dynamic and static load, right? The static load which is not changing with respect to time, either magnitude or directions. But here in the dynamic load, either magnitude will change or direction will change, or both will change, then it is coming under dynamic load. For a completely reverse load, the failure stress, we know that. No. What is the failure stress? Endurance strength. This we know. This is the failure stress. But when the material is subjected to static load, let's say the material is subjected to static load only. When the material is subjected to only static load, then what is the failure stress? If it is a ductile material, if it is a ductile material, we know that failure stress is yield strength. If it is a brittle material, we know that ultimate strength. That is the failure stress we have. But what happens when this particular component, let's say the same component, but now let's say we have the hole in that component, and this is subjected to P to P by 2. It is being subjected to P to P by 2. When you see the load, sometime it is P, sometime it is P by 2. Kind of this, the loads are acting. So in this case, my dear friend, when you calculate the static load as well as dynamic load, both will be coming into the picture here. Because of this, there will be mean stress and there will be variable stress will also be acting. Both are not equal to zero. Here, both mean stress as well as variable stress will be there. What I'm saying, when the load is not changing, only it is P. Let's say static load P is constant. Then tell me what is a variable load? What is a variable load? The variable load means sigma maximum. Oh, sorry. Here we are calculating the load. So P maximum minus P minimum by 2. Here, when the P is constant, there is no variable load. There is no maximum minima. Everything is zero. P variable is zero, right? But when the component is subjected to completely reverse, like it is changing from minus P to P, minus P to P. So here P maximum, let's say we have P, and P minimum we have, let's say, minus P. Then what is the P minimum? P mean. P mean, which is responsible for static failure, 0. But what about P variable? We have particular what? P value. We have what? Particular P value. So here, in case of variable loads, in case of completely reverse load, mean stress is 0. Mean stress is 0, mean load is 0, then we don't talk about any static failure. We talk about dynamic failure. But when we have only static load, we talk about static failure here. Static failure. But in this case, you know that when the load is changing from P maximum, that means here P maximum is what? P, and P minimum is what? Let's say P by 2. Now you know that P variable you can calculate. What is that? P minus P by 2 divided by 2. That means it will be P by 4. And when you calculate P mean, that is also P maximum plus P minimum divided by 2. And now when you put the value P plus P by 2 by 2. So 3P by 4 will be the answer. So now it is both 0. Both are not equal to 0. That means what? Both will be present. Static failure and dynamic failure. And under those situations, you know that under those particular situations, you know that what will be the how to calculate the failure stress. The failure stress in this case is not known. So for that case, we use different criteria. Sometimes we say Soderbergh criteria, Soderbergh line. Sometimes we say Goodman. Sometimes we say Gerber criteria. So that's why we plot the graph. A general graph I'm plotting. Y-axis we are taking what? Variable stress. X-axis we are taking what? Mean stress. On the x-axis, variable stress is 0. When the variable stress is 0, the failure stress, you know that yield strength. For example, if I'm considering the example for ductile material, then what I'm doing here, on a x-axis, I'm plotting mean stress. Mean stress means here mean stress. What is the failure one? The failure one will be yielding strength. What about the variable strength? What about the variable stress? On the y-axis, we have variable stress. Mean stress is 0. When the mean stress is 0, what is the failure stress? Sigma e. Now, when you connect the dot between these two, you will be getting the plot something like this. For example, if I draw the graph for Gerber parabola, what you are observing, when the mean tensile stress, see, it is on the first coordinate. This particular graph is what? In the first coordinate. First coordinate means what? Tensile stress will be there. There is no chance of compressive stress. When the mean stress are tensile in nature, and when this mean stress is keep on increasing, that means tensile force keep on increasing. Now you tell me whether endurance strength is increasing or decreasing. When you look from the graph, when you keep on increasing the value of the mean stress, you are moving towards the right side of the graph. when you are moving towards the right side of the graph, your endurance strength is keep on decreasing. See, correspondingly, in sigma E is what? Keep on decreasing. What is the meaning of this? When endurance strength is keep on decreasing, what is the meaning of these things? Endurance strength should be high or low. Always remember, endurance strength should be very, very high, right? When the endurance strength is decreasing, that means within the fraction of second, a small amount of dynamic load, it will fail, right? So chances of failure will also increase. Chances of failure will also increase. So what you are observing, the mean tensile force is causing a difficulty for us. The mean tensile force is a culprit here to cause the fatigue failure, right? Chances of failure means what? Fatigue failure will increase. Fatigue failure will increase. Fatigue strength will decrease, right? Fatigue strength will decrease. So what you're understanding from all these circumstances that when I increase the tensile force, the chances of failure is very, very high. And you know that one graph, whether you know or not, I don't know, but we also know this is a value of sigma E. We also know, my different the compressive stress. Like if I take the second coordinates, and when I just increase the compressive strength, mean compressive strength, when I increase the mean compressive strength, I will be getting the graph something like this. So what you're understanding from here, if I keep on increasing the if I keep on increasing the mean compressive strength, mean compressive stress, if I keep on increasing the mean compressive load in the component, then there is a no effect of endurance strength. Then there is a no effect on endurance strength of a component. That means what? The component is not failing because of compressive stress. The component is failing. The fatigue failure of a component is happening because of the tensile force. So by any chance, we have to look for a method which can reduce the tensile force, which can increase the compressive force in a material. That's why we use some method called cold working operation called short peening, or we can say burnishing operation. We also perform some other operations, note down. So now you understand why we are using that. See, note down. To increase fatigue life of a component, first method we follow here, surface treatment operation. Surface treatment operations like, see here, we got the answer, right? We got the answer within fraction of second. Don't think that we are taking too much time. Here we are taking time to understand which is and why we are using this particular method, right? This is the cold working operation, right? This is the cold working operation, and in that too we try to introduce the what? Compressive is we try to introduce compressive load in that particular component, right? By using this particular short pinning process. Surface treatment operation like nitriding, carburizing, cyaniding. Then we have case hardening. Then we have case hardening. These are the processes that will increase the fatigue life of a component, right? Then we have cold working operation. We have cold working operation. Note down. We have the cold working operations. Cold working operations like short pinning, right? Short pinning. These are the method to provide residual compressive loads, right? Before coming into the functionality, right? What this do? This provides residual compressive load. By any chance, see, the mean tensile force, let's say you have certain value, let's say you have plus 30. By any chance you have introduced in a component any compressive load, by compressive load compressive stress will be developed, let's say it is minus 5. So automatically you are reducing 20, 30 to 25 or not, right? If you are reducing anyhow, that means what, you are moving nearer to this particular graph, that means you are not moving towards right side, you are somewhere here only, right? That means endurance strength is what, having significant values, right? So that's what I'm talking about right here. Here, by using the cold working operation, we are introducing the residual compressive loads or compressive strength of a component has been increased. Now, what is the short pinning process? Let's say any component we have, any ball, right? If I'm talking about any very random operations, so there is a ball which is being thrown at a very, very high impact force on this surface of a component, right? So when this component is impacting with this surface of a component, then it will introduce some kind of compressive load. Because of the compressive load, some plastic deformation will happen. Because of this, some plastic deformation will happen, and then it is bouncing back again. So because of this operation, the residual compressive strength of a component has been increased. When it is being subjected to some operations where it is subjected to fatigue dynamic loads as well as static load, then whatever the endurance strength will be there, that will not reduce that much. Always remember, in reality, the material is subjected to both dynamic load as well as static load, and the failure can happen because of both fatigue failure and static failure. But sometime fatigue strength of a component is too very very low. In such a case, even though before static failure, fatigue failure will happen in a component. Static failure may not happen, right? Static failure. See, what is the meaning of static failure? In a ductile material, you keep on applying tensile load, it will fail, right? That is a static failure. In case of fatigue failure, what will happen? You keep on applying too much amount of dynamic load so that it will what? Whenever any component, let's say we have the hole in a component, right? Then what will happen? The crack will be appear and the material will break at that particular point. That is a fatigue failure, right? Or what will happen here? So this fatigue failure will happen much earlier than the static failure, right? So we have to be very, very precautious against both the failures. We have to stop both the failures, right? Sometime it may happen that fatigue failure may not happen, but static failure will happen. So we have to stop that also. So in those circumstances, we have to do some operations so that we intentionally try to introducing the compressive stress, because you know that the compressive stress will not cause anything on endurance strength of a component, right? Even though you keep on applying the mean compressive stress, right? But endurance strength is what, constant. This is the horizontal line. Whereas you see mean tensile stress, because of this, it is subjected to what, decreasing endurance strength. When you just increase the value of load in such a way that when it is exceeding the value of sigma by t, already endurance strength is what, nothing you have. The failure phenomena already begin, right? Not on the third operations, what we call, by using auto fittage technique. This auto fittage technique we use, auto fittage technique, we use it for thick cylinder, where cylinder is subjected to what, winding of the wires. In that case also we are introducing the compressive load indirectly, right? So no doubt the main objective of short pinning is to improve the fatigue strength of a component. So this auto fittage technique also being asked in ISRO, one of the previous year questions. So whenever you are reading any book, suppose you are reading VV Bhandari, you try to read all the pages of that books. Let's say fatigue, you are reading the fatigue load chapter in that. So now you have to focus on both numerical as well as theoretical, right? So you try to read the theoretical part of that book also, not only the numerical part, because from there only they are taking the question. These are the questions that is not coming from the sky. All the questions are from the textbook only. Remember that. Now, the next question which we have to take here is that which thread is more suited in power screw to take the load on both the directions? So, in the last class also we have seen some types of thread. There we have seen the acme thread, which having the thread angle 29 degree, where we have the included angle is what, 29 degree. In this case also, and when you take the square thread, where threaded angle is 0, both the flanks are perpendicular. Here you will see square threads, acme thread, which is a special kind of trapezoidal thread. Actual trapezoidal thread, when you ask me, having included angle 30 degree. Do not confuse. Don't say trapezoidal thread we only have acme thread. Acme thread is one of the special type of trapezoidal thread. Actual trapezoidal thread, when somebody will be asking you what is the included thread angle, then you must say included thread angle is what, 30 degree, whereas here we have 29 degree. Trapezoidal trapezoidal threads. It is one of the types of trapezoidal thread, right? And here we have the butter thread, where included angle is 45 degree. The problem here with the butter thread, just like a screw jack, whatever the screw jack is there, you know, whatever the screw jack is there, there we have threads. In the screw jack, we have threads. Let's say, for example, let's say we want to lift any machine, then what we use, then we rotate in one particular direction, then we are able to lift the machine. If we want to lower the machine, we can just rotate in other direction, so that we can lower the machine by using that thread. So square thread and acme thread, these both the threads are there which can transmit the load in both the directions, which can transmit the load in both the direction, or which can transmit the power in both the directions. Note down. Square and trapezoidal threads can transmit the force and motion in both the directions. Can transmit force and motion in both the directions. Whereas butter thread, the profile is such a way that when you try to see, imagine one situation where the butter thread is being used in screw jack. Again, that is a very foolish kind of thing. You cannot use, but forcefully, if you are using the butter thread in screw jack to lift the machine, to lower the machine, any component, then what will be happening? Suppose when you are applying the load or rotating the suppose this component in one direction, you might be able to lift the component, but while lowering the machine, it will be already what, interlocked. It cannot do that. So butter thread, it can transmit the force and motion only in one direction. No doubt. Again, if you are thinking that, sir, I'm not getting the feeling how and why, please try to see YouTube animation of butter thread. There you can understand why it can only transmit the force and motion in one direction, not in both the directions. It can transmit power and motion only in one directions. No doubt, this is a very, very important. What is this 29 degree? We call this to be thread angle. So whenever you are reading anything, let's say you are using you are studying the chapter power screw from the BB Bhandari, you try to read all the pages of that book, make a short notes of that, and try to note down everything about the thread profile and all. What will be the standard value of the pitch, they can ask in examinations, right? Who knows that? Anything they can ask. Previous year, by the help of previous year question, you can only take advantage. You can see, okay, what are all the things they can ask, right? Up to what depth they can ask the question. That's it. If you are expecting that the previous year question will be repeated, that is not going to happen. And my prediction is that it will never happen. In upcoming examination, which will happen after 1.5 months, it will not even maybe you find 2 3 questions. Apart from that, no question will be repeated from the previous year questions. You can only take the idea, but you have to read thoroughly about those the topics which are already being asked in previous questions, right? Now, here the next question is belonging to strength of material. So here in simply supported beam loaded as shown in the figure, they are asking what is the maximum bending moment. So the very similar kind of problem of transferring the load from the bracket to the beam we already discussed, right? Here in the last session also we have discussed. Let's say we have B, D, E, that is a bracket. Through this particular bracket, we want to transfer the load 100 Newton to this beam. What we have to do, we have to introduce two equal and opposite load at the joint where the bracket and beam is connected. At a joint where the bracket and beam is connected, where it is connected at B. So you try to introduce two loads. One is 100 Newton here, one is 100 Newton like this. Because see, ultimately 100 and 100 will cancel out. No problem, right? No problem in introducing the two equal and opposite loads. Ultimately, they will cancel out. Right now, finally, again, this is not only the method. This is a very shortcut method to do that. Again, you can do if you want to do exact method, then you have to draw free body diagram of DE member, DB member, then ABC member. That is also there, but unnecessarily you will waste the time in examinations. You need not to do any kind of PhD work there. Shortcut you have to follow to get the answer within fraction of second for a question which is not that much lengthy and very simple, right? So here when you transfer the load, this is the A, this is B, this is C. We have simply supported ends. And at B, what will happen? This 100 Newton will be acting, no doubt, in the downward direction, but this 100 Newton and this 100 Newton will make a couple in which directions? In this clockwise directions of the magnitude of 100 into 100 Newton mm. See that? This one and this one will create a couple in these directions. That will also going to transfer at point B. Now we got to know the load which is being acting on a beam, exact loads which are acting on a beam, that we know. Now what we can do, we can transfer, or we can, what we do, we can just calculate the reaction force. So what is the reaction force? Ra and Rc. Ra plus Rc, we know that that is 100 by using summation of forces in the y direction to be 0. Now we take summation of moment about A to be 0 by static equilibrium conditions. Then we can write Rc into 1000. Then we can also write here, see, this is acting in the anti-clockwise directions. 100 Newton, 100 into 100 Newton mm is clockwise. 100, which will be caused by this 500, will also be acting in the clockwise. So both I am taking what? Towards the right side. So 100 into 100 plus 100 into 500. So you will be getting what? Divided by 1000. So RC, you're gonna get 60 Newton. What about RA? RA, you're gonna get 40 Newton. RA, you will be getting what? 40 Newton. Note down. Then what we have to do? Now we got RC as 60, RA as 40. Put those values. Now, what is the bending moment diagram? I'm drawing over here. So this we got to know 40 Newton. This we got to know 60 Newton. 100 Newton, and there is a clockwise couple is also acting. Now, what is the A, B, C? What is the bending moment which are acting at point A? That is 0. Bending moment at the ends, always 0. What about bending moment at point B, just to the left of B? Left of B means I'm moving from here. So I'm just taking here. So we can see only this part of the beam. You cannot see any kind of external movement when you just consider left of the point B. So 40 into 500 Newton mm. But they are asking in Newton meter. So better to divide by 1000, so that you will be getting what? Newton meter only. Newton meter. So you will be getting what? 20 Newton meter. What about the bending moment just to the right of B? Just to the right of B means you are at the right side of the point B, where you can see whole world of the beam, where the load is acting, moment is acting, and all those things. So 20 automatically will be there, but there is a movement you can see, and that is acting like a sagging bending moment, that will be added. So 100 into, again 100 divided by 1000, we are converting in Newton meter. So you will be getting what? 30 Newton meter. So by this you can see here, suddenly there is a jump. Why there is a jump? Because of clockwise movement which are acting at a point B. Then you can draw like this. So here it is 20, and then we have 35. Sorry, 30. So whenever at any point two bending moments are acting, so always you have to take maximum of that. So what is the maximum value? Newton meter, 30 Newton meter. So which option is correct? B is correct. Again, very similar fashion questions. They are repeating from 2015 to 2016. Right. So this is a bending moment diagram. You can move from here to here also, right to left also. I have taken from left to right, left to right. You can also move from right to left. Again, you will get the same answer. Now have a look on this particular questions. Two steel rails which are being length of 12 meter. The length is given as what? 12 meter. Are led with a gap of 1.5 mm at the ends at a temperature of 24 degrees centigrade. The thermal stress produced at a temperature of 40 degrees centigrade will be what? So there is a gap of lambda 1.5 mm. So basically, this case is something. If I take example, this case is belonging to something like this. Let's say the length of each rail is L, and you have certain gap between the supports and the rail is lambda. When you try to increase the temperature of this bar, for example, it will try to expand, and it will try to hit that particular right support. But here the right support is somewhat kind of flexible support, not a rigid support. Of course, it has certain gap of lambda where it can only permit the deformation up to lambda, not more than that. It can permit the deformation up to the lambda, not more than that. Whereas we have seen the certain cases where it is fixed at both the ends with the no provision of any kind of expansions. This case, the complete deformations, the complete deformation is what? Zero. Either thermal or mechanical, both the deformations are zero here. But in this case, whatever the deformations are there, let me write deformations delta, total deformations. The total deformation by anyhow, it has to be lambda only. That's it. Now, in this total deformation, we know that mechanical deformation will be there and thermal deformation will be there. Thermal deformation, because the temperature is being getting changed. Mechanical deformation because of when it is trying to hitting this right support, the right support will say hello, you go back, and it will offer some kind of reaction force, and because of this reaction force some mechanical deformations will gonna happen. So here thermal deformation, everyone know that alpha into delta T into L, that is the thermal deformations, where alpha is what, coefficient of thermal expansion, which is being given in the question. Then thermal mechanical deformation is what, the reaction force which is being offered by that support, RL divided by what, A, because you know that mechanical deformation as PL divided by AE, right? Here the load is what, R, that is equal to what, lambda. So here R value, if you just try to calculate, so what you can get, alpha into delta T into L minus lambda whole bracket AE divided by L. That is a reaction force offered by that support, but we are not interested in calculation of reaction force. Very much interested in calculation of thermal stress. That is nothing but R divided by A. R divided by A. So here when you write thermal stress, alpha into delta T into L minus lambda into E by L. So now when you put those values, alpha is what, 12 into 10 power minus 6. Delta T is what? Now the temperature got changed from 24 to 40. So 40 minus 24. The length is what? 12 meter. Everything you try to convert in mm. So it will be 12,000 mm. Minus lambda is what? 1.5. Into E. What is the E value? E value is what? 200 or 2 into 10 power 5 Newton per mm square. Length is what? 12,000. So you try to calculate and tell me the answer. 12 into 10 power minus 6 into 16 into 12,000. That value is what? 2 point. This particular value is what? Coming as 2.304 minus 1.5 into 2 into 10 power 5 divided by 12,000. So you'll be getting what? 13.4 Newton per mm square. And what should be the nature? The nature should be compressive stress. How you will decide whether compressive or tensile? Because the reaction force is what? Is compressive force offered by that support. When the temperature will increase, compressive stress will be developed. When the temperature got reduced, when the temperature got reduced, then tensile stress will be developed. But you have to observe very careful. Here they have not given any option called 0, but they can give the option called 0 Newton per mm square also. Why? If at all, you have to look at the condition where alpha into delta T into L, this particular value should be more than lambda. Then only any kind of stress will be produced in a component. If you are thinking that, even though you don't have if you are thinking that, here put a note, you have calculated if alpha into delta T into L is less than lambda, that means whatever the provision for deformations is permitted, but your bar is not able to expand up to that much of length, it is only able to expand up to this much of length, then why the support will offer some kind of reaction force? Why the support will offer some kind of reaction force when it is not disturbing? No reaction force, no thermal stress. So always you have to check whether alpha into delta T into L is more than lambda or not. Right? Even it is just equal also, then also the what we call thermal stress will be 0. No doubt. Now, when we move on to the next question, see, an aluminum tensile test specimen has a diameter D naught 25 gauge length 250 Now, in a specimen, when you see the any specimen which is undergoing the tensile testing machine, that is a universal testing machine UTM, you will have certain gauge length. We don't take total length of a component for our total length. We are not taking into the account. We are taking only the gauge length, right? Where the test and the results will be expected. Other length apart from the gauge length is there for the gripping purpose, right? So that is the meaning of gauge length, right? Suppose in examination, if they will give the total length of a component is 300 the total length of a component, and they will give certain call, and certainly the same question they will be asking you, right? And they will be giving you the length which is used for the gripping purpose is 50 Then definitely you have to subtract 300 minus 50, that is 250 we have to take it as a gauge length, right? Because they are asking, it is being getting elongated by 1.25 This elongation will happen here P into L naught divided by AE, right? So this L naught is what? My dear friend, this is a gauge length. Whatever the formula we are using, that is a gauge length, not a total length. If you are using total length as 300 then you will be getting wrong answer for E, Young's modulus, right? So please make a note of those things also. So 1.25. Now during those eras, 2016, 15, maybe you can see that much of level of paper was not expected. Though the competition was high, but still the paper basically kept by ISRO was not that high standard. But nowadays when you see the recent papers of ISRO, they are highly standard papers. Hardly you will see anything from regular questions. So you have to be thorough. You have to prepare for the worst conditions, right? So 1.25 the load is acting what? The force of 175 Newton. Gauge length is what? 250. Area is what? Pi by 4, 25 square. Young's modulus is what we have to calculate. From here, you can calculate Young's modulus. You will be getting approximately 71 point. Check it out. 71.30 something you will get into 10 power 3 megapascal. That means you can write 71.3 gigapascal. A is correct. See, in a universal testing machine, you will have upper jaw. Here you have the lower jaw. You will have the component which is being there, something like this. This will be pulled. You know, if you are applying the testing machine, and here we have the results which you will be getting in the form of paper graph, right? Whatever the graph is there. So that is the upper jaw we have and the lower jaw. In between that, the component is getting fixed and it is being loaded with the tensile force. You have to be very fast in calculations. You will not be provided with any kind of calculator. Modulus of elasticity, we also call Young's modulus of what? Elasticity. Now we'll move on to the next question. Again, this question is belonging to strength of material, that is the power transmission. A shaft is there which is being used for power transmission, because you know that until unless the shaft is being rotated, we cannot say that shaft is useful shaft. If shaft is stationary, then what is the purpose of that shaft? No purpose of that. If it is rotating, it is transmitting the power from motor to the any other component, then we say the usefulness of any shaft. So same thing is being reflected in this question. They are asking a tubular shaft which is having certain like a hollow circular shaft which is having some internal diameter 30 mm and outer diameter as 40 mm. It is being used to transmit the power of 80 kilowatt. The speed of rotation of the shaft they are asking so that the shear stress will not exceed 50 megapascal. So from the shear stress, we know that what is the formula we have? We have the torsional formulas. Torsional formula, by the help of torsional formula, we can calculate T by J, tau by R naught. So here we can write tau max, that is T into R naught divided by J. If we are calculating tau max, then R naught will be considered. If we are interested in tau minimum, then inner radius will be considered. So here what will be there? From here we can calculate torque. From here we can calculate some value of the torque, because power formula we know that torque into omega. We can also write 2 pi nt by 60, where n is what? In RPM. If you want to calculate n in RPM, then for that you need torque. And how we can calculate torque? We can calculate torque from these equations. T will be what? Tau max into J divided by R naught. So we can write 50. J is what? Pi by 32 d naught power 4 minus di power 4 divided by r naught is what? We can write d naught divided by 2. R naught we can write d naught divided by 2. So from here what you can calculate? T you can calculate 50 pi divided by 32 into 2. Then you can write here d naught q 1 minus di by d naught 30 by 40 to the power 4. Because d naught to the power 4 I have taken outside, it will cancel out by denominator d naught. So in the bracket term will be what? 1 minus di by d naught to the power 4. That's what I have written. So from here when you calculate torque, you will be getting 429.5146 Newton meter. Remember, you will be calculating in Newton mm. First convert that in what? Newton meter. Here you will be getting, let me write in terms of 10 power 3 Newton mm. But when you divide by 1000, you'll be getting what? Newton meter. Check it out whether you are getting same or not. D naught you can keep it as 40. So once you got to know T value, 429.5146 Newton meter. Now you can calculate power 2 pi nt by 60. That is a very basic question which is being repeated in many examinations. Shaft power is given was 80 kilowatt, 80 into what? 1000 watt, 2 pi n. T is what? T is 429.5146 divided by 60. So from here if we calculate n, that is coming as 1778.621 RPM. C will be correct. Note down. Again, do not think that I cannot do by hand calculation. All the things are possible with the hand calculation, but my suggestion will be this type of question you have to do at the ends when you complete all the other questions, so that you can come back to this question and solve and get the what solution for these questions. Only the thing is that you have to remember polar moment of inertia for a hollow section. Now coming back to this next question, a cantilever beam is subjected to load P at a distance of L by 3 from a free end. They are asking what is the deflection at the free end. That means a cantilever beam is being subjected to the load at a distance L by 3 from the free end. L by 3 here, let's say B, C, A. This is L by 3, this is 2L by 3. The total length of the beam is what? L. They are asking what is the deflection will happen. So what will be the deflection curve? If you are able to plot the deflection curve with the help of elastic curve, you know, very easy you can get the answer for this question. So they are asking what is the deflection at this point, right? So that is a very easy task. Only we have to calculate what is no theta b and deflection at b, because delta c will be theta b into L by 3 plus deflection at b. Because what is the tan theta b? You can also write theta b when theta b is very very small. That is equal to this distance, let's say y, divided by L by 3. So y will be what? L by 3 into theta b. This is nothing but y plus delta b. That will give me total delta c. But these things we got to know from the elastic curve. But this elastic curve, how we plot it? This particular elastic curve, how we plot it? That is a very simple thing. We know bending equation, right? What is the bending equation? M by I, sigma by y, E by R. M by I, sigma by y, E by R. When you calculate the radius of curvature from here, you will be getting E I by M. When you look at B and C section, at any section you calculate the bending moment. In the B and C, the bending moment is what? Zero. The radius of curvature will be infinite. For which curve we have the radius of curvature infinite? Straight line. That's why we have plotted what? Straight line here. But when you see A to B we have the radius of curvature that is variable. See A to B, the bending moment is what? Varying. When the bending moment is varying, when we will be getting the radius of curvature as parabola, because for parabola we have varying radius of curvatures. That's why we plotted parabola. But at a junction point B, the slope offered by this and this straight line will be what? Same. That's why we are using what? Same theta b for calculation of delta c, right? So here, what is the value of delta b and theta b? That is the very standard results we have. A cantilever which is being subjected to point load having a length of 2L by 3. What is that formula? PLQ divided by 40, PLQ divided by what? 16 EI. So PL, length is what? 2L by 3. C, a cantilever beam subjected to point load P having a length of L. What is the deflection formula at C? We know that PLQ divided by 3EI. PLQ divided by 3EI. But here length is what? 2L by 3. For this our standard case. So P into 8L cube divided by 81 EI. That is the deflection one. Theta B will be P into 2L by 3 whole square divided by 2 EI. So now when you calculate, so you will be getting 4P L square divided by 18 EI. Now put those values of delta B and theta B, what you can calculate. Again, those who are not able to digest this elastic curve method, simply they can follow, there are many methods, what we call moment area method, We also have strain energy method. It's up to you, whatever you want to follow. You can get the same answer as we are getting by this method. So delta C will be theta B is what? 4 pi L square divided by 18 EI into L by 3 plus 8 pi L cube divided by 81 EI. So after all this calculations, you will be getting what? 4 pi L cube divided by 54 EI plus 8 pi L cube divided by 81 EI. So when you take LCM of both 54 and 81, you will be getting what? 81. So here you can write 6 plus 8 PLQ. From here you can get 14 PLQ divided by 81 EI. This will be the answer for delta C. Simply you feel that this is a very tough, then you can get the answer by using moment area method also. Let me explain the moment area method also. Moment area method. See here, this is the what we have question. First of all, plot what we call bending moment diagram. When you plot the bending moment diagram, you will be getting the bending moment diagram like this. PL 2PL divided by 3. This is the way of bending moment diagram. But we are not interested in bending moment diagram because we are very much interested to know what is the M by EI diagram. That is bending moment diagram divided by EI. So ultimately, you will be getting the graph somewhat smaller value than this. So here you will be getting 2PL divided by 3EI. Now, once we know the bending moment diagram, now you can calculate the deflection at point C. How to calculate deflection at point C? You know that two theorems are there under moment area method. First statement is there to calculate slope. Other statement is there to calculate deflections. When you see the theorem number 2, by theorem number 2, delta C, you can write delta C, that is equal to moment of area delta C with respect to A, right? Moment of area of M by EI diagram between A and C about C. When you read the statement, I'm not repeating statement once again here, but when you see the statement, they have written that if you want to calculate deflection at any point, if you want to calculate deflection at any particular point, then what you have to do, you have taken the 2 points on this elastic curve, you have plotted the elastic curve like this, right? Then this is the point C, for example, and see, we are drawing this slope at a particular point A. Draw the slope, this will be the slope at point A. Or we can write here tangent. We can write tangent of a particular slope at A. This is the tangent at A. And if I plot here, this will be the tangent at C, the tangent at C. So what is a statement? They are saying that they are saying the difference between these two tangent we call delta C with respect to A. And what is this particular value? The distance between this particular tangent and this particular tangent. I'm not confusing you. This is an official statement which is being given in Gary and Goodnow. If you don't want to confuse yourself, you simply do not remember the statement, you simply follow these things. Whenever at any particular point you want to calculate deflections, take a moment of that area of M by EI diagram which you have calculated. This is M by EI diagram which you have calculated. Take the area moment of that area. What is the moment of that area? First calculate the area of this particular M by EI diagram, because there is no area, so that will be 0. Only area will be what? Half of base into height, 2PL divided by 3EI into what? 2L by 3. And take the moment of that area from the point C where you have to calculate uh, this particular pot deflections. That is the statement into X. But how to calculate X? Now from here to here, what is the centroid of this? That is 2 by 3 of 2L by 3. And what about this? This is nothing but L by 3. So we can write here 4L divided by 9 plus L divided by 3. So here we can write, this will cancel out. So this will be 2PL square divided by 9 EI, plus here we can calculate 9, 4L plus 3L. So ultimately, once again, you will be getting what? 14 PLQ divided by 81 EI. That is deflection C with respect to A. Automatically, that is a deflection C only. Because tangent at A is horizontal one. There is a no slope at A. Theta A is 0. Deflection at A is 0. And that is being what? In the downward directions. So either you follow elastic curve method or you follow this particular method, moment area method, you will be getting the same answer. Right? The meaning of moment is that whatever the area is there, that area centroid perpendicular distance. Because what is the moment? Force into perpendicular distance. Here you will be getting the force in the form of area of M by EI diagram. Area of M by EI diagram, that will give you something kind of intuition. It will give you the value of kind of force into the distance, right? Distance from which point? Not this A point. Distance from centroid of this to the point C where we are calculating the deflections, right? So that is the moment area method, and that is what we have seen this method. This is very simple method because we know standard results, right? Theta B and delta B. Now coming back to this machine design problem, note down. Now this problem, first time they asked in 2016, that was again, those who have not read all the VB Bandari pages very carefully, they cannot able to solve this question. Because all the time we talk about dynamic load capacity of the ball, but here the question is belonging to static load capacity. Very clearly they have given the formula in the form of Streeback equations. When you just go through the VB Bhandari book, then they have given very clearly about the bearings, ball bearings is Streeback equations. That's why I'm saying that I'm requesting you to follow all the pages of particular VB Bhandari textbook if you want to follow for machine design. All the questions will be there in ICRB 2023 examination from that textbook only. If they want to frame somewhat good level question, then definitely they will take the question from that book. Otherwise, simply they will copy paste from other examinations. And those other examination questions are also from this VB Bhandari only. Now, so note down Streeback equation. Note down Streeback equation. Streeback equations. What is the Streeback equation we have? Streeback equations. C, we represent it by C, static load carrying capacity. We represent it by C, that is a formula we have K d square z divided by y, where K is what? Constant. Again, remember, you might have followed dynamic load capacity of the ball bearing, but this question is belonging to static load capacity of the ball bearings. T is nothing but diameter of the ball. Z is nothing but number of balls. Number of balls. I will tell you what is the meaning of static load capacity, but first of all, we will solve the problem. If the ball bearing, the number of balls is reduced to half, that means Z2 is what? Z1 divided by 2. The diameter of the ball is increased to 4 times. Then what about this static load carrying capacity? Here C naught we got this much. Then C naught 2 will be what? K into uh, D2 by Z2 divided by 5. K will be constant anyhow. D2 is what? 16 times of D1 square. Z2 is what? Z1 divided by 2 into 5. So now when you look at this one, then C naught 2 will be what? You will be getting 8 times of K D1 square Z1 divided by 5. Whereas K D1 square Z1 divided by 5 is what? 8 times of C naught. What we have seen that here. So it is being increased 8 times. D will be correct. But the question mark, sir, I have not understood what is the meaning of static load capacity. Let's look at that. Note down. Note down. What is the meaning of static load carrying capacity? Note down. Static load capacity. You know that the ball bearings are there. They will be subjected to lot of amounts of load during its functionality. Static load required to produce the permanent deformation in the balls and the races at the most heavily stressed point of contact equal to 0.0001 d, where d is diameter of the ball, right? What is the definition? Because you know that the ball bearings, when you look at the ball bearings, here when you see the races of that, in between that you have to place a ball. These balls will be subjected to loads. During its functionality, they will be subjected to loads. There is no doubt about that. So, what is the meaning of what we call static load carrying capacity? Hold on. Static load, because you also know that because of the load, deformation will happen. But how we define the static load for this ball bearing? No doubt. In fact, for the anti-friction bearing, no doubt, static load required. Static load required to produce permanent deformation. To produce permanent deformations in the ball, in the races also. See, what is the meaning of race? This is the ball. This is the outer race. See, here if I just say the ball will be under cage. Cage I have not drawn because of the limitations. So here this is the outer ring. Right. This is the inner ring. I draw with a different color. You have here inner ring, inner ring, Here you have outer race. Then again you have inner race. So not only you have permanent deformation in the balls, but the permanent deformation will also happen in the races also. Whatever the races you are observing, this black color, there also there will be some deformations. So static load required to produce the permanent deformation in the balls, and races. Races are the place to put the balls in a space in that particular position, so that the balls will not be scattered during this movement of the ball bearings or during the motion of a particular shaft. In the balls and the races, at most heavily stressed point of contact, point of contact equals to which equal, what is the equal? Static load required to produce the permanent deformation, which is equal to 0.0001 t, right? So what I'm saying here is static load required to produce the permanent deformation in the balls and the races at the most heavily stressed point. See here, this is a very important. At a see, you know that the failure will happen in a component where the material or the component is subjected to highly stressed value. Whenever at any point very high value of the stress will be there the failure will happen. Same thing they have repeated here. The static load required to produce the permanent deformation in the balls and the races at the most heavily stressed point of contact when it is equal to 0.001 d, where d will be equal to diameter of the ball in mm, right? Because whatever the diameter is there in mm, so whatever the deformation is there, that will also be in mm. If that deformation is equal to this deformation, this particular 0.0001 d deformation, then we say the whatever the then we say that during those deformations, at that particular deformation, whatever the load which can be bared, which can be sustained by that ball bearings, we say that is static load capacity, right? Static load capacities. So these are the static load capacity of a ball bearing. Because see, some of you might be thinking, sir, why only we consider only ball? Why we are considering only for the, not only for the balls but the races also? Because if the race will also be failed, automatically balls are going to be what, not in a position what we have seen, and if they are not in a proper position, they will not be able to support the shaft, right? Ultimately bearings are what, bearings are basically a member, supporting member, which basically supports the other rotating elements, just like what we've seen, the rotating element of kind of what, shaft, right? Note down one more important thing here. Not only we have the static load, what we call static load rating, static load capacity of the ball bearing, we also have static load capacity of roller bearing. Because you might have seen in the data book of design data book of ball bearings, you might have seen that you have C naught, you have CD also, that dynamic load rating as well as static load rating, right? Ultimately I want to say, when the shaft is subjected to, when the shaft is rotating, then whatever the loads is produced, dynamic load rating. When the shaft is stationary, during those circumstances also, it is not like that the component will not fail, because it is not rotating during those condition also. Because of shaft is being stationary, there may be chances that the ball may getting deflected or displaced, there will be some deformations. Here for this, for those cases also, we define static load capacity and dynamic load capacity, right? Note down C naught will be k dzl divided by 5, where d is nothing but diameter of the roller. Now here it will not be d square, because here, my dear friend, a roller is what? Something like this, where we have diameter d and the length of a roller. Z is number of roller bearings. Next time they will be asking you the question about the roller bearings. If the diameter will be getting, let's say the same question, if I talk about same question, the diameter will be getting 4 times of original diameter, and the number of roller bearings, let's say half of that. Now in this case, C naught will be K times of D2 will be 4, half of that into DZL divided by 5. So here it will be 2 times of C naught, not 8 times. It will be 2 times, not 8 times for case of roller bearings. Now, those who want to understand completely, very fundamentally, the concept of anti-friction bearing, sliding contact bearing, then you can follow or you can join the IGC basically what classes, or you can follow IGC notes, right? Each and everything are given in detail about the bearings. Like, see, two things are there. If you want to learn the concept directly by heart the formulas, get the answer. But if you want to get the feel of why the question has been framed, if that type of question will be coming in your mind, then you are in the right directions. That means you are not only understanding why the questions has been asked, what why there is a necessity of those questions with respect to design point of view, right? So these are the things which are very very important. Why the static load rating is there, why dynamic load rating is there. In the last class we have seen that, what we have seen. I told you the formula, load life equations, right? C divided by PE to the power q for a ball bearing, where C is nothing but what? Dynamic load rating, right? That is also why it is coming dynamic, why static. Those are the things, those will be cleared when you understand each and everything fundamentally. And if you want to learn, then you can join IGC classes or you can follow IGC notes, right? So that is about this question. They have given the ball bearing questions. If it is a roller bearings, it will be 2 times for the same question, same data. So the last problem we will see here, a theoretical one here. Try to see the match the following options. That's a pretty straightforward, but some of the concept we will try to learn in detail. That is like a resilience. What is the modulus of resilience? What is the proof resilience? All those things we will learn here. See, a resilience, when you say, then capacity of the material to absorb energy elastically, right? So I'm telling you right now, option A for 2, that is correct. Fatigue, what is the meaning of fatigue? The failure of a material, the failure of a material at a loads less than the normal condition. I told you, right? Normal condition is what? Static condition. Sometimes fatigue failures are happening much earlier than the static failure, right? Those statements they have kept in the form of options here. So B will be 5. Stiffness, what is the meaning of stiffness? A resistance of a material, the resistance of a material to elastic deformations. That is the stiffness, right? So C will be for 4. What about elasticity? Then everyone know that a perfect elastic material is that which can able to return to original shape when the load is being removed. So what is the graph? When you see here stress versus strain diagram, you will find like this. When the load is getting, suppose you have loaded this material, when you remove the loads, it will follow the same path. That means there will not be any plastic deformation begin in the material. Complete shape can be regained. But even though slight deformations, plastic deformation will happen, that may trigger and that may cause some of the what we call plastic deformations here. The shape will follow here. The path, when you remove the load, it will follow like this, B to C. When there is a slight plastic deformation, if there is no plastic deformation till here, when you load this one C dash, then it will follow the same path as a C dash, right? So first of all, we will learn what is the meaning of resilience. So we got the answer. Answer is D. But we are not bothering. We are not so satisfied with the options or the answer. We will try to go into the deep of the definitions, and we will see what is the meaning of resilience. If anyone know, they can answer. Or if any doubt till now, they can ask here. No doubt. Ability of the material to absorb elastic strain energy. No doubt. Ability of the material, or we can say it is defined as energy absorbed energy absorbed by the material within the elastic region. Within the elastic region. There is a one term also coming always, prove resilience. It is defined as maximum energy absorbed by the member within the elastic region. Within the elastic region. Right? That means if somebody will be asking you how to calculate prove resilience, then you have to say area of P versus delta curve, area under P versus, or we can say P versus lambda curve or delta curve here up to the elastic limit. Whatever this area will be there, that will be prove resilience, half of P into delta. Sometimes we also say modulus of resilience. We define one term, modulus of resilience. It is nothing but prove resilience per unit volume. Prove resilience per unit volume. And it can be calculated from area of stress versus strain diagram. No doubt. Calculated from area under stress strain diagram up to the elastic limit. Whatever the elastic limit is there, whatever this area will be there, that is the modulus of resilience. So many questions they can ask from this page if they want to ask. Modulus of resilience, again, that is the property of the material. Resilience or proof resilience, they are not the property of the material. property of material. Again, there is a one more term called toughness. Energy absorbed by the member just before its fracture point. Energy, total energy absorbed by the member just before its fracture point or up to the fracture point. We say toughness. Here we are defining the resilience where energy being absorbed by the member up to the elastic region. We are not extending our limit from elastic to plastic limit. Actually, when you see stress versus strain diagram, you will not only have elastic limit, you will have plastic limit also. See here, whatever the deformation is there, here to here, we have plastic deformation. Till here, whatever the deformation, we have elastic deformations. So in a material, we do have both elastic and plastic deformations, but we are not bothering about plastic deformations. Here we are not bothering about anything about the plastic deformation. Whatever the energy being absorbed by the member here, that will be my modulus of resilience, and whatever the energy being absorbed by the member, total energy area under this total curve will be modulus of toughness. Again, modulus of toughness is basically the property of material because it is independent of length and diameter of a component. So that is regarding the resilience, right? That is what they have given. Ability of the material to absorb certain amount of energy within the without failure, right? Without failure. That is nothing but no. That is not correct. Resilience means capacity of the material to absorb the energy elastically. This word is very important. So third is incorrect. In fact, third is not correct for any other options. You know, fatigue. What is the meaning of fatigue? Fatigue means failure of a material at a loads less than the normal conditions. I told you. Stiffness, ability of the material to resist the elastic deformations. Elasticity. What is the meaning of elasticity? When you load the material, there will be certain deformation, but when you remove the load, it will able to regain its shape and size. That is called perfect elastic material, right? But as I told you, in reality, we do have elastic deformation as well as plastic deformation. So even though let's say you have loaded till this point, now when you remove the load, it will follow this particular path. So there will be certain amount of, let's say this is what we call total plastic deformations. This will be your elastic deformation. You will have certain amount of here this is nothing but total deformations. You will have certain amount of plastic deformation that will be retained in a component, right? That will be retained in a component. But when you load the material till here only, and when you try to follow, this will follow this path. And during that, you will only have elastic deformation. You will not have any kind of plastic deformations, right? But that is a very kind of rare case. So I hope you understand the fundamental what we learned today. So that is all about 2016 paper. Next, we will try to learn the we will try to solve the paper of 2017. The subject will be same: strength of material and machine design. Right. Thank you all.